So let's look at some special cases, examples of special cases in this, when you're having a maximum or minimum with two variables. You have like a, an LP basically. See how we can graphically determine the four types of solutions and such. But anyway, there's four cases when solving an LP, as we've been doing. We have unique solutions, infinite number of solutions. Unique solutions is what we've had, the couple examples we've seen. Then you have infinite number of solutions, which is alternative optimal solutions is the proper term, I guess. Because really it's not, I don't think it's always going to be really infinite. It's more like just a set of solutions, like a bunch on one line. And like a segment, a line segment, so there's a definitive beginning and end of it. But there is an infinite number if you go down, if you can count all the fractional forms and everything. Count all of them. Either way. You have no solutions, which is also called an infeasible LP. And you have an unbounded solutions. Yeah, so unlike a linear system of equations where there's three possibilities, there's actually four possible solution types with LPs, as we are seeing. And the unbounded solutions is a very specific case, especially when we are dealing. It can be seen with minimums, but it's really only seen with maximums where we look at, because we're usually bounded by the first quadrant, and usually a minimum would then not have this condition. But anyway. There's a problem, an example that shows it, but here's a bounded solution example. We have a maximum problem of z and unbounded solutions, and it's unbounded solutions because we have everything. This is the feasible region. It's all out here, and with a minimum, it would be probably it would be a point. It would be likely this point or that point. One of these 2 points would give you the minimum. Or that point, basically you'd have very few. You'd only have a few options to consider. Here it's maximum z, and it moves toward unbounded part of feasible region. The solutions. Z, so it keeps on getting bigger. So your maximum will continue to get bigger and bigger the further you go out. So it's unbounded region, which has unbounded solutions. And there'll be an example of that as well. So let's see. But that example is just a quick sketch of one idea to get an idea, because unbounded solutions is one of the more unique things, if you will. So what case applies to each of the following LPs, and we have four of them. So first is x1 plus x2. So we basically just solve this, get it graphed and see what it is. Try to solve it like normal. Yeah, but it's written clearly. I think we have. Yeah, it checks out. We get intercepts 0, 4, 4, 0, and 0 plus 0 is less than or equal to 4. So that means 0, 0 is included. x1 minus x2 equals 5. 0, negative x2 equals 5, so x2 equals negative 5. x2 equals 0 and x1 equals 5. So you have 0, negative 5, and 5, 0 as your intercepts for the green. 0 minus 0 is greater than or equal to 5 is not true, so 0, 0 is not, the point 0, 0 is not included. And we have to remember x1 greater than or equal to 0 and x2 greater than or equal to 0, and you're going to see that constraint failed. There's no case where this passes. So the pink I even shaded in briefly in the green, and they collide here, where it's very obvious. And if you really wanted to, you could calculate the intercept of these 2 points, since they obviously intersect. But it's pretty, this graph was done carefully enough that it's pretty obvious that they don't. They don't intercept in a positive region of the x1, x2, where you have a coordinate. You have even one possible coordinate that could be positive. So yeah, basically the pink and the green, so basically the combined areas where I'm putting in a little bit of black in. So it's all negative values of at least one zane. So basically we'd have x1 be positive, but x2 negative would be a good way to say it. It's the constraint that has those two be positive. It fails because you need both of them to be positive. So it's an infeasible, that implies it's an infeasible linear program as there is no solution which satisfies all constraints. And that's a good way to briefly look at the infeasible idea of an LP. Yeah, we graphed these carefully and you can see there's nothing that you can do. Even showing the shading of those, which I normally don't, but like the pink and the green is in the area they overlap. The area of overlap can be called. Where the feasible region is down here and it has negative x2 values. x2 is never positive, therefore there's no feasible solution. There's no. What would be the feasible region is not a feasible region because it's infeasible. Here's one. So let's go try to look at something better. So you have max z equals 4x1 plus x2, such that these constraints 8x1 plus 2x2 less than or equal to 16, 5x1 plus 2x2 less than or equal to 12, x1, x2 greater than or equal to 0, of course. You solve it, you get 0, 8, 2, 0 as our intercepts, and of course 0, 0 point is 0 plus 0 less than or equal to 16, so we include it. 5x1 plus 2x2 equals 12. You get 0, 6, and 12 fifths 0. And the 0, 0 coordinate will, of course, also be 0 plus 0 less than or equal to 12 you get, ultimately, so it checks out. So we include, so we find that quadrilateral ABCD is feasible region. By graphing them, and you get purple star and red star, so it's this point 0, 0 included, so it's just areas. So it's this little shaded region. And we know point A, and we know point C, and we know point D, we just need point B. 0, 6, because that's an intercept, 2 zeros, and intercept, and 0, 0 is obvious. It's also a sort of intercept. So now we have to do a little very basic algebra to figure out intercept. So we do equation 1 minus equation 2 when we set this up, because it just gives us 3x1 equals 4 and 5x1 plus 2x2 equals 12. We just divide by 3 to get x1 equals 4 thirds, and we plug that in. X1 equals 4 thirds, and we plug in 4 thirds for x1 and then solve for x2 eventually. We get 8 thirds as we simplify down. So 4 thirds and 8 thirds are a solution. That's the point of intersection. So we have the max z equals 4x1 plus x2. So we plug in each time, we get 4 times 0 plus 6 equals 6 for A. Point B gives us 8. Point C gives us 4 times 2 plus 0, which is equal to 8 as well. And D gives us z equals 0. So in pink I highlight this so we have two maximums. So B and C are maximums, both they give us the maximum solution, and according to Siri, it's the points that give the maximum. There's no other points that'll give it. So all the 4 points that we have are what one of them will give us a maximum. So we got two maximums now. So the solution equals the whole BC segment, and that means it's alternative optimal solutions answer. And real quick we can show, so 8x1 plus 2x2 equals 16 would be the line that contains the solutions, because it is a line. So x2, you can solve this for x2, which would be y normally, like a lot of times it'd be x and y, so you can think of it like that in terms of x and y. So x2 equals negative 4x1 plus 8. And we also know z equals 4x1 plus x2, which means x2 is just equal to negative 4x1 plus c. So the slope of the objective function here would be equal to the slope of the isoprofit line isoprofit line, which is what this in pink is, like x2 equals negative 4, x1 plus 8. The isoprofit line, where it's all the same values, maximum. So maximum of z equals 8 across the whole line. But that's the whole idea. Yeah, that's just a note you can do. You don't usually have to go to end-ups. You can just say it's the whole segment BC and its alternative optimal solutions, and that's pretty good. But it's good to look at it like that. Yeah, that's another example. So we have 2 more cases to look at an example of each. I mean, unique solution we've done before, but we'll see. So 3, we have max z equals negative x1 plus 3x2, and the constraints such as this. x1 minus x2 equals 4, we get basically none. 0, negative 4, 4, 0. It checks out the point 0, 0. Again, was x1 plus 2x2 equals 4. You get 0, 2, 4, 0, and 0, 0 point does not check out. So it would be up about this. So we include 0, 0 for red and don't include it for purple. So in the end, we get this whole region. It's a maximum z, and it looks like this. So it's unbounded linear program. And if we want to, we can mess around a little bit. We know the point A is 0, 2. We can also figure out the point B. It's unbounded, though, anyway. We can do the basic stuff. But here's the first thing to note, the main thing. So it's unbounded linear program is the important point. Max z equals negative x1 plus 3x2. So x1 decreases, x2 increases is what the idea would be for the maximum value somewhere. It goes on infinitely, though, in theory, this whole thing. But x2 will get at very large, well, yeah, basically x2 will at very high values get a bigger objective function. And that's what you can say about this unbounded linear program. Is that the general trend is that very high values, you'll get higher and higher values as x2 increases. Is a very general trend. So the B point is x1 minus x2 equals 4 and x1 plus 2x2 equals 4. We solve. It's very easy to solve because one of them is equal to 0. So max z equals 6 or max z equals negative 4. No, but these don't work because it's unbounded. You could take any values in the whole feasible region and it'll give you, there's a lot of values that'll give you much bigger than these. That's true. And keeps on getting bigger and bigger and bigger. The objective function will never be maximized truly. Because it keeps on getting bigger and bigger, so it's unbounded. Unbounded linear program. But that's the difference between a no solution or infeasible LP and an unbounded in idea. And now finally we'll do just one was a unique solution because that's the only one we haven't looked at for this section, but we've seen them in the other section. Last section when we solved 2 different LPs, we saw how distinct they are. How the unique solutions, there's only one solution. So we have max z equals 3x1 plus x2. 2x1 plus x2 equals... Yeah, basically we do the solutions, red and blue here. We include the point 0, 0 for both of them. Well, then we get intercepts and graph it as nicely as possible, like here. I think one of my more accurate graphing methods. In like scaling, I scaled the x and y axis, x1, x2 axis pretty well. And anyway, we have a quadrilateral ABCD again as our feasible region. Because we included 0, 0 for both of these lines, so it goes down. And we know point A is 0, 3, point C is 3, 0, and point D is 0, 0. So we calculate point B and we get eventually we get 9, 5, and 12, 5. I mean 9 fifths and 12 fifths. So we do z equals for b, is in a, c, and d, so b first. Z equals 3 times 9 fifths plus 12 fifths. You eventually get 27 plus 12 over 5, so 39 fifths. We have that point A, which gives us just 3. Point C gives us 9. Point D gives us 0. It's a unique solution because I, in orange, put C as that largest value. And you notice, because if you do 39 divided by 5, 40 divided by 5 is 8, 39 divided by 5 is just 7.8. You do it in your head like that. But yeah, you can do it on a calculator. And basically 7.8 and 9, 9 is the bigger number. So we have one maximum. In a maximum, we want the biggest value, basically. So unique solution, x1 equals 3, x2 equals 0, and z equals 9. So quick as a quick. And finally, let's just do a quick true and false. True or false? For an LP to be unbounded, the LP's feasible region must be unbounded, and this is a true statement, of course. This is a very true statement. You need LP to be unbounded, the LP's feasible region must be unbounded. This is very true. As you saw as that example as well, it makes sense somewhat just thinking. It's true when you think about it in every case. Is this stated by fact max z must increase so we never leave feasible region, and that min z must always decrease so it never leaves the feasible region for that LP to be unbounded. So basically, it can't leave the feasible region is the big idea. So in examples, we have max z here in green, the feasible region stuff. Z increases up, z decreases down if it's brown here, feasible region, minimum bound. And I have x and y are some inequalities fitting the LP's constraints. So we have our two main, let's say we just have two constraints. X is a constraint, y is a constraint here. The idea is that you have the feasible region here and the feasible region there. And it goes minimum z here, it just keeps on going down. Feasible region here just keeps on going up. At the very least, that's a big part of it. And there's other situations, but of course, it's just a basic, it's a true statement, and it's just a good idea to give an example a lot of times. Sometimes help explain it like this. And that's all for this idea of the special cases.